Hello, this ERTMS ETCS Learning Module 7 is regarding the online key management system for supporting the operation of ETCS Level 2. The contents of this learning module was prepared by Christopher Coe and will be presented with the voiceover generated from the synthetic voice technology. This module mainly covers the OKMS concept in ETCS Level 2 environment, and the expectation of the ETCS technical specification for interoperability, TSI. There are many abbreviations in this module, each of those will be revealed throughout the module. This module will cover the purpose of the KMS, the concept of OKMS, KMAC, KMC, TLSPKI, and the certificate authority. At the end of the module, there will be an overview of the OKMS architecture, and the relevant specifications documentation. There are several introductory slides to go through, then there will be diagrams to explain the principles of the OKMS. The ETCS Level 2 operation uses open transmission systems to transfer messages between the radio block center and the trains. These data messages include the movement authorities and other critical information, which are fundamental to safe train operation for the ETCS Level 2. The data transmission over Open Radio Communication Networks (GSMR) is inherently vulnerable to unauthorized access if the data is unprotected. Therefore, it is important to secure the integrity and the authentication of the messages sent over a non-trusted transmission medium. The ETCS applications use cryptographic techniques, with secret keys, when transferring data. A system is required for cryptographic keys to remain secret, and to be installed in the correct ETCS radio block center, and the onboard unit. When transmitting the cryptographic keys, the keys are protected by the other cryptographic keys. The Key Management System, KMS, is the collective term for the personnel, the equipment, and the procedures used to manage the cryptographic keys. The GB industry has decided that there should only be one key management system, KMS, for the GB ETCS mainline railway. Network Rail is the administrator of the GB Key Management Center, KMC, for both offline and online key management configurations. This was considered the simplest, and the most efficient solution, for minimum number of interfaces, and lower risk associated with the ETCS security features. This diagram shows the basic elements for the ETCS Level 2. The onboard unit, OBU, is the ETCS element on board the train. The GSMR is the transmission medium. The radio block center, RBC, authorizes the train movement with authorization from the interlocking system, ILS. The traffic management system, TMS, initiates the authorization of the train movement automatically, or by the human. Only the OBU and the RBC are relevant in the context of the OKMS, because only the data between these two systems requires protection with the key, KMAC. The current key management practice is offline, known as the offline key management system. The offline KMS does not abbreviated into OKMS. The key management for Cambrian and Thameslink are offline method. The offline method requires very simple software and computers. However, managing the keys offline is labor-intensive. In simple term, the software known as KMC, Key Management Center, generates the secret key, known as the KMAC, and encrypted by the transport key, KTrans. The abbreviation KMAC will be explained later in this module. The human copies the file into portable storage, such as the USB memory stick. Then, hand it over to another human, who has access to the OBU or the RBC, to copy the KMAC file into the OBU or the RBC. Both the OBU and the RBC need the same KMAC, so that both can communicate with each other securely. Before putting a new OBU into service, new KMAC needs to be added into the RBC. Likewise, when there is a new RBC, new KMAC needs to be added into all the onboard units, supervised by that RBC. When the KMAC is known compromised, the KMAC in the RBC and all the onboard units require updating. This diagram shows these 8 trains are within the RBC1 area, and will be operating in the new RBC2 area. All these trains will require the KMAC matches the RBC2 KMAC for the communication. The process of adding, updating, and deleting the KMAC from the RBC, or the large number OBU of the ETCS Level 2 trains, is labor-intensive, which also means costly. Next section of this module will walk through the basic concept of the KMAC. Let's assume the message transmission between the radio block center and the onboard unit is not encrypted. The message is in 1 and 0, which means nothing to a human, or the computer that does not know the message format. However, the ETCS specification is published on the Internet. Anyone can find out the format, and the structure of the message. The unencrypted message is exposed to the man-in-the-middle attack. For example, this Amber person could intercept the blue message that contained max speed of 50 km per hour. Then, this person could change the value to 90 km per hour, and resends the message again to the train. The message still contains the ID of the RBC, so the train will not be able to detect the message has been tampered with. Subsequently, the train will action on the higher speed value. To prevent the man-in-the-middle attack, the message will be encrypted with a code known as KSMAC. KSMAC is the code generated based on the KMAC for that particular communication session. KMAC stands for Key Message Authentication Code. KMAC is not a cipher, it is a code for encrypting and decrypting the message using the chosen cipher. In network security, KMAC is known as symmetric key. Anyone who has the symmetric key can decrypt the message, which encrypted with that key or code. So far, we know the message needs encryption. So, what is OKMS? What is the role of OKMS in ETCS Level 2? In very simple term, OKMS is a system for sending secret in secret. Later, there are more slides explaining how OKMS fits in the ETCS. Let's put ETCS to one side, and jump into the virtual world of secret agents. Hopefully the secret agent scenario is easier to understand. Here, there are 2 secret agents, A and B, sending secret message to each other with the super-strength metal envelope and padlock. Both agents have the identical blue keys. Agent A puts the message in the envelope and locks it with the blue padlock. Agent A puts the mail in the post. When Agent B receives the mail, Agent B uses the blue key to unlock the blue padlock. If the Amber person intercepts the blue padlock mail without the blue key, the Amber person will not be able to open it. So this is quite simple and straightforward. When the secret agent team gets bigger, there are many secret agents that need to send secret messages to only certain agents but not all. The agents will have to find a way to manage all those different color keys, and knowing who has what color keys. They will need key management. Key management is the generation, storage, secure distribution and deletion of secure keys. The secret agents need a secret agent HQ. The HQ is also known as the Key Management Center, KMC. KMAC stands for Key Message Authentication Code. In this case, KMAC is the name of the key that the secret agents use to unlock the padlock. Hence, these secret agents are also known as the KMAC entity. Now the HQ transports the correct color keys to the correct agent via a truck. The HQ knows who needs what color keys and who has which color keys. Next problem comes, the amber person is back. This amber person can swap the keys at the back of the truck. All the secret agents will receive the keys from the amber person rather than from the HQ. The amber person keeps the keys and unlocks the padlocks later, when the HQ sends out secret mails. So, how could the HQ transport the secret key in secret to stop the amber person from swapping the keys? Here is where the confidentiality comes in. Confidentiality is to prevent information from being read by unauthorized entities. The secret agent world needs three things: a safe, a padlock and a key. From here onwards, to keep it simple, I use only one secret agent for explanation. The safe is called TLS. The padlock is called public key. The padlock key is called private key. This key is not the key called KMAC. The whole infrastructure is called TLS-PKI, stands for Transport Layer Security Public Key Infrastructure. The secret locks with the public key cannot unlock by the public key. It is like a padlock, it can lock the safe, but cannot unlock the safe. The private key is used to unlock the secret, but not to lock the secret. It is like a padlock key that cannot lock the safe, but only for unlocking the padlock. In the computer world, the computer does not care whether something is called public key or private key. Both are just a bunch of numbers, as long as one of the codes is used for one purpose only. The names public and private are for human to understand when configuring the system to avoid human mixes up the keys. From here onwards, I refer to safe, padlock and key. Hopefully this is easier to understand. First, the HQ agent asks the secret agent for a red padlock. Secret agent posts the red padlock to the HQ agent but keeps the red key. In the computer world, this public key does not have to be encrypted because it can only lock the message and cannot unlock the message. The public key is useless for the attacker. The private key is the important one. Next, the HQ agent puts the blue KMAC key in the safe and locks the safe with the red padlock. The amber person is back again attempting to steal the blue key. Only the secret agent has the red key for the red padlock. Assuming the safe and the padlock are made from the super strength metal. The amber person cannot get the blue key without the red key to unlock the red padlock. When the safe arrives, the secret agent can unlock the red padlock with the red key to retrieve the blue key. But, how does the HQ agent know the padlock was from the secret agent? The padlock could come from the amber person who pretends to be the secret agent. What can we do to this problem? Here is where the authentication comes in. Authentication is to allow the receiver to confirm the message is in fact from the indicated sender. The secret agent world needs a trusted bank and a padlock certificate. The bank is also known as the CA, stands for Certificate Authority. The bank is the trusted third party for the HQ agent and the secret agent. The role of the bank is to verify the identity of the padlock owner. The bank will use various methods to verify the identity of the secret agent and the ownership of the key for the padlock. Here are some photos showing the real-world situation. The verification process is called root signing ceremony in the Internet world. A group of people is within a Faraday cage checking the identity of the Internet domain owner and the digital keys. The cage is there to prevent someone copies the private keys and transmitting out wirelessly. Now back to the secret agent world. The secret agent registers the padlock with the bank. After the bank confirms the identity of the agent, the bank issues a padlock certificate. The certificate contains the identity of the agent and the padlock serial number. In the Internet world, the certificate contains a lot more information. There is a slide later showing the digital certificate. When the HQ agent wants to send the secret agent the blue KMAC key, the HQ agent asks the secret agent to post over the padlock and the certificate. The HQ agent recognizes the certificate and details match the secret agent such as hair color, skin color, blood type and height. The HQ agent can also check the certificate details with the bank again. The secret agent must never ever send out the red key, known as the private key. The amber person will not be able to get a certificate from the bank because the amber person would not be able to prove the secret agent identity. Of course, the bank can be compromised if the amber person attacks the bank, or the bank issues certificate without thorough checks. It did happen in the Internet world. The Symantec CA was caught issuing illegitimate certificates, resulting in Google, Apple and Mozilla revoked all the Symantec certificates. DigiCert acquired Symantec CA later. Then the CEO sent out the private keys via email, resulting in 23,000 customer certificates revoked. After the HQ agent is happy with the certificate, the HQ agent puts the blue KMAC key in the safe and locks it with the red padlock. The safe can then transport to the secret agent on the public road just like the public Internet network. When the safe arrives, the secret agent can unlock the red padlock with the red key to retrieve the blue key. The infrastructure with safe, padlock, padlock key, certificate and the bank, is known as TLS-PKI, stands for Transport Layer Security Public Key Infrastructure. TLS-PKI is for ensuring the blue KMAC key is secure during transport. The bank is the heart of the whole TLS-PKI. If the bank is compromised, the whole system is compromised. In the larger scale with multiple secret agents, each of them will send their padlock certificate to the HQ. The HQ will then put in the correct color KMAC keys in the safe, and locks it with the correct color padlock. Only the agent holds the key, which is same color as the color of the padlock, will be able to unlock the safe, to retrieve the KMAC key. The agents with the same color KMAC keys can then communicate with each other in secret as many times as they want. The red agent communicates with the green agent using the blue key, and communicates with the gray agent using the amber key. The HQ agent and the bank do not get involved in their secret communication. Let's go back to the ETCS Level 2 world. There are two roles within the TLS. TLS stands for Transport Layer Security. The roles are the TLS server and the TLS client. There are three KMS entities in the ETCS Level 2. The Key Management Center, KMC, the Radio Block Center, RBC, and the Onboard Unit, OBU. The KMC can be in the server role, or the client role, depending on which system establishes the TLS connection first. The TSI only expects the RBC to be in the TLS server role, and the OBU in the TLS client role. The Key Management Domain, or KM domain, covers one KMC and all the RBCs, and the OBUs registered to that KMC. The RBC and OBU can only register to one KMC. The KMC outside the GB main line is described as the foreign KMC. The descriptions of the home and the foreign are from the RBC or the OBU perspective. The KMC in the Y domain is the home KMC for the RBC or OBU registered in the Y area. But KMC in the Y domain is the foreign KMC for the OBU registered in X area when operating in the Y area. Although RBC does not move around, the OBU under the RBC supervision could be from another domain. The RBC needs the matching KMAC for the communication. The OBU can move around, it can be in different KM domain. So, the KMC is responsible for generating the KMAC, for the RBC registered to the KMC. But the KMC is responsible for generating the KMAC, for all the OBUs operate within the KMC area, including those registered to the foreign KMC. Let's forget about the home and the foreign for the moment, when looking at the TLS-PKI server and client relationship. The authentication is based on the certificate issued by the certificate authority. This is the bank in the secret agent world. The TSI only expects the OBU plays the TLS client role, and the client certificate is optional in the TLS-PKI. Hence you don't see the OBU in this diagram. The CA, certificate authority, is the PKI server for the certificate process. Both the KMC and the RBC are the PKI client. The PKI client generates the public and private key pair, which are the blue key and blue padlock, before contacting the PKI server. The client sends the certificate request message and the public key to the server via CMP, the Certificate Management Protocol. The server already has the root or master certificate for each system that the human verified the owner of the public key for the system. So, the server sends the digital certificate, embedded with the public key, back to the client. The KMC or the RBC has the private key, public key and the certificate. The certificate is not a one-off process. The human can revoke the certificate in the CA server if there is a security breach incident. For example, the private key of the KMC or RBC is compromised, like the incident I mentioned earlier, about the private keys sent out via email that ended up revoking 23,000 certificates. In simple term, if there is a chance of someone could have made a copy of the blue key, the blue padlock becomes useless. So, the client needs to check the certificate status is not revoked, by sending the OCSP request message to the CA server at regular interval. The TSI default value is 10 hours, but can be set from 1 to 100 hours. For efficiency, the OCSP, Online Certificate Status Protocol, allows the client just checking the status instead of asking for new certificate every 10 hours. The CA server sends back the OCSP response with one of the three status. The status is either good, revoked or unknown. For TLS connection, the client contacts the server rather than the server contacts the client. This is same as the Internet website connection. Our browser is the client contacting the website server. In the OKMS setup, the KMC is the client for the RBC, the OBU is the client for the KMC. This means the KMC contacts the RBC, but the OBU of the train contacts the KMC. For home and foreign KMC connection, the KMC that is making the request will take the client role. So, the KMC can be a client or a server, depending on what task the KMC will be doing. The server role will have the digital certificate and the public key, which is the padlock. The RBC does not have to contact the KMC on regular interval, hence it is assigned as a server role. The OBU only makes TLS connection when it needs to contact the KMC. There are 4 situations that the OBU will contact the KMC. The OBU TLS client establishes connection with the KMC TLS server after the OBU is switched on and the startup tests completed successfully. Or, after the predefined time elapsed, with the default value sets for 10 hours, or the time can be set in between 1 hour and 1000 hours. The connection is also initiated after the maintenance staff requests OBU to update the KMAC key. Or, after the OBU detects a corrupted or invalid KMAC key. The first message the client sends to the server is called client hello. Just like making phone call, we usually say hello first. The computer does the same. The client hello message contains the client-supported ciphers and requesting the server certificate status. The server then responds with server hello message with the selected cipher. The server also sends the digital certificate to the client. The certificate contains the certificate status that the server already obtained from the CA. The certificate also contains the public key, which is the padlock, for the client to use. At this stage, the client has the public key from the server. The server keeps the private key. Defining the server and client roles in the system is important, because this will define which side has the private key. For practical reason, we also don't want the private key in the OBU, because there will be hundreds of trains moving around with the private keys. The server and the client will generate the session key based on the public key. You may wonder why generate another key since both sides have the public keys. The public key is a padlock that cannot unlock the message. The connection is for two-way communication. The server needs to send data to the client as well. But the client only has the padlock that cannot unlock the message. The session key is known as the symmetric key. It can be used to lock and unlock message. The session key is only valid for one connection. This avoids the same key is used again and again. The more times the system uses the same key, the higher chance for someone to figure out the key. The client will send the session key encrypted with the public key to the server so that the server can confirm both sides have the matching session key. Encrypting the session key is to prevent someone intercepts the session key and later communicate with the client. Only the server can decrypt the session key because only the server has the private key. When both the server and the client have the identical session keys, both sides are ready to transfer KMAC in the secure manner. The session key is the padlock and also the padlock key, that can be used to encrypt and decrypt message. After the TLS connection is established, the definition of the server and the client roles don't matter that much. The data transfer can go both ways, server to client or client to server. The KMC will encrypt the message with the session key. The message contains the KMAC. KMAC stands for Key Message Authentication Code. The KMAC only comes from the KMC. The message also contains commands such as add key, delete all keys or update key. When the RBC or the OBU receives the message, it will decrypt with the session key. Then take action based on the command in the message. After the RBC and the OBU have the same KMAC, both will use the KMAC to encrypt the ETCS messages between the RBC and the OBU. The KMAC will be used again and again, until the validity period ends. The TSI does not mandate minimum validity period. The validity is depending on the purpose of the KMAC. For example, if the KMAC is intended to test a train with the RBC for 2 days, the validity period can set to 2 days. After the date and time expired, the OBU or the RBC will detect the KMAC is invalid and will not transmit ETCS message with the invalid KMAC. Is the TLS connection bespoke for the ETCS or OKMS? No, it has been around in the Internet world for about 25 years. The initial one was called SSL. SSL stands for Secure Sockets Layer. The TLS for OKMS version specified in the TSI is version 1.2, which is more than 10 years old in the Internet world. The latest version for the Internet is 1.3. The Internet is also using more up-to-date cryptography. The OKMS behavior is same as our Internet browser and the web server. In this simple example, our browser is the client, eBay computer is the server. When we put in eBay address in the browser sends client hello to the eBay server. The eBay server then sends server hello, digital certificate and public key back to the browser. The browser verifies the certificate and extracts the public key. Then the browser encrypts the new pre-master key with the public key and sends it to eBay server. Only eBay server can decrypt the pre-master key, because only eBay server has the private key. The pre-master key will become the session key. After that, the browser can send the encrypted credit card number to eBay server. eBay server will decrypt it with the session key. So, how does our computer know the eBay certificate is legitimate? The computer does not know and the computer does not contact the CA either. The browser knows. Our browser is pre-installed with all the trusted CA information. This slide shows a list of trusted CA in the browser. The browser validates the CA signature in the eBay certificate with the trusted CA information. Otherwise, there will be millions of browsers contacting the CA server every second, and the Internet will fill up with the traffic just for validating certificates. The OKMS setup is slightly different to the Internet setup, in terms of the relationship with the CA, because there is only one CA for the owner of the ETCS Level 2 infrastructure. This is an example of the digital certificate from the eBay server. OKMS will have the same format, it is called X509 certificate. The certificate will state who is the CA, the validity period, and the public key. The cipher suite is a set of algorithms that help secure a network connection that uses TLS. The key exchange algorithm is one of the algorithm sets within the cipher suite. The key exchange algorithm is a cryptographic algorithm. The TSI requires the TLS server and the client to support at least 4 cryptographic algorithms. The elliptic curve Diffie-Hellman, ECDHE, the Rivest-Shamir-Adleman, RSA. The Galois counter mode, GCM, and the secure hash algorithm, SHA-384. Let's take RSA cryptosystem as an example. RSA is the abbreviation of the first letter of the last name. Of the 3 computer scientists and mathematician, published the RSA algorithm in 1977. These are the 2 equations for the RSA encryption and decryption. E value in the encryption equation is the public key value. D value in the decryption equation is the private key value. These are the steps to calculate the public key and private key. First, select the large prime numbers p and q. The p and q must not be the same prime number. Then, calculate the RSA modulus n value by multiplying p with q. Next, calculate the totient of RSA modulus n by multiplying the p-1 value with the q-1 value. After the totient of RSA modulus n is calculated, select the e-value, that is an integer number, smaller than the totient of RSA modulus n, and is a coprime to RSA modulus n. The e is the critical value for the public key. The final step is calculating the d value by solving the equation. After the mathematic calculation, we will have three numbers, e, d, and n. These numbers become the public key and the private key. A quick example here, with all the numbers calculated. The unencrypted plaintext is H. After encrypted with the equation, the ciphertext is 28. The receiver can then decrypt the ciphertext 28, with the decryption equation to reveal the plaintext H. This is the basic concept of the public key and the private key from the computer perspective. The final section of this module will walk through the fundamental system architecture for OKMS. As an overview, the Online Key Management System, OKMS, covers the client or server part of the KMC, the RBC, the OBU, and the CA. The KMC is the TLS client, TLS server, and PKI client. This is in the same hardware, just like our computer can serve as a client and a server. The RBC is the TLS server and the PKI client. The OBU is the TLS client. The CA is the PKI server. The home KMC requires interface with the foreign KMC. The foreign KMC can be the online, or the offline KMS for its own domain. The KMC, the RBC, or the OBU is called the Key Management System Entity, or the KMS entity. Only the RBC or the OBU is called the KMAC entity. The KMAC only exists in the KMC, the RBC or the OBU. But not in the CA. The abbreviations and terminology of the online key management system can easily cause confusion. There are many terms use the word key. Some abbreviations are quite close, such as the KMC and KMAC. But, these two mean completely different elements in the system. Here is the list of the abbreviations mentioned in this module. KMS stands for Key Management System. OKMS stands for Online Key Management System. Offline KMS stands for Offline Key Management System. KMC stands for Key Management Center. KMAC stands for Key Message Authentication Code. Also known as the ETCS key. KSMAC is the session key. KMS entity means the KMC, the RBC, or the OBU. KMAC entity means the RBC, or the OBU. ETCS entity means the KMC, the RBC, or the OBU. ETCS entity means the RBC, or the OBU. TLS stands for Transport Layer Security. PKI stands for Public Key Infrastructure. CA stands for Certificate Authority. Asymmetric keys means the public key and the private key. Symmetric keys means the session keys. So, where are the OKMS specifications documented? The CCSTSI subset 137 is the main specification document for the OKMS. Those TLS, PKI, OCSP, X509 and the cipher are not specified by the railway. These are in the Network Security RFC specifications. In addition to the requirements in the TSI, the UK Digital Railway has additional requirements for the GB OKMS. Here are the few key items. The OKMS requires to be online 24 hours for 365 days per year. Support 10,000 onboard units. Support 500 radio block centers. Establish TLS session every 24 hours with the RBC. Transmission via IP, GPRS or EDGE bearer. Key management via remote access, and including the offline key management system. Finally, the same question again, what is OKMS? In one simple sentence, the OKMS is a system for managing KMAC, and to deliver KMAC in a secure way. This brings us to the end of the ERTMS ETCS Module 7. In summary, this module shares the key information of the key management system, the architecture of the online key management system, and the principles of TLS/PKI. Thank you for your interest and attention. Goodbye and have a good day.